Anyway, but don't worry about it, I'm rewriting the homeworks and tests, and so I'm only talking about that because I'll be a little bit more careful. You folks, in some of the questions you had for me, I saw where I could have done things better. Anyway, but let me point out, let me just do a quick review on some of the things I noticed in the discussion we had on the homework, which was, it goes back to this whole eigenvalue equation when it kind of fails, right? So we know that, let's do a free wave function, let's call it a sine wave function. Sine, when I say free wave, I mean totally flat potential, the thing I hope you're sick of now. We know that sine does something really funny. It's fine because the double derivative of sine is sine, and so that gets a pass on the kinetic energy on momentum squared over 2m, but then it failed when I applied momentum, which is strange. And I told you we'd figure it out later, which we did. But now that you've learned a bunch of things, I can point out a bunch of things to you at once. Remember how I said you have to know like 5 things at once to understand this stuff? Which is really awkward because I have to go through them one by one. Okay, now recall that when we did uncertainty, if you have an uncertainty problem, you expect this behavior. But you don't have an uncertainty with momentum squared momentum. So the fact that this apparently has failed, right, these are not equal, this eigenvalue equation has failed is like impossible. Because p squared, remember that sine is okay with p squared, which is energy basically, and momentum, those do not have an uncertainty principle. This should pass, but it didn't. Why? It turns out you're just not doing it right. Now again, I'm just reviewing. The solution is to apply the operator, but as to take sine and put it into a sum of things that are eigenfunctions of momentum, that you know are eigenfunctions of momentum, and those of course are e to the ikx, e to the minus ikx. So you can see, so you can do that, and then you can snarkily get the expectation value out by, the first guy is easily an h bar k. Now remember that the next guy, you bring down a minus ik, but you would end up with as a minus, right? So what you see is, you still see your sine function, e to the ikx minus e to the minus ikx, so there's your sine function. But then you see that the momentum components are plus and minus, and they sum to 0, right? So that was a snarky way to show how to do this. Now also recall that when I put this ostensibly failing representation into this, what I did was I used that to show that you can always solve this with the average value way. Right, the reason that this works is because you can take wave functions and put them as a function, as a sum of wave functions of the ones that do work. So sine doesn't work, but it's a sum of wave functions that do. And you can either solve it this way, which is way easy, and it's what I really want you to do on the homework because it's way easy. You can do it this way as well. And note that when I showed that this worked, I actually used this as part of the proof. So anyway, just wanted to review. Now, so because some of you ended up trying to solve, when I really wanted you to do it this way, some of you tried to do it this way, and it does actually work. It's just way harder than I really wanted. I didn't want you to do that, it's way harder. But anyway, so I'll just add something on the enter key for that. So now, one reason I'm harking on that on this last homework is, and I'm going to review a lot for the present homework for this lecture. The reason I harped on what I did on this last homework, so you notice the last homework was all about these expansions, because God forbid any of you actually go to grad school. This is the most insanely useful thing about quantum mechanics. It's the only thing I actually kind of enjoy about this. It is fairly frequent that I can use a supercomputer to solve a wave function, and the damnedest thing is unbelievably complicated. But it can be decomposed into miniature solutions that aren't hard at all. And then I can get answers, and I do it this way. So again, I often, professionally, I don't do quantum mechanics professionally often, to be honest. I'm writing homeworks a lot of the time, but I often, sometimes when I am doing quantum mechanics, I'll use a computer to solve a wave function, and it's so unbelievably complicated, I don't even know what to do with it. So I break it down into its components, and then I solve things this way. And it's way easier. And again, this is actually something I do professionally. And I wanted to point out that the coefficient, actually, I can't remember if it's the coefficient or the coefficient squared. I'm blanking out right now, and maybe I got that wrong on the homework, but regardless, these things are called overlap integrals, and that's where you get the coefficients. Now, one of you asked me, oh, wait a minute, I thought this is either 0 or 1. And that depends whether these are the same wave function or not. Okay, now that actually depends on, you have families, right? So when you have a Hamiltonian, you have a family of wave functions that are solutions. So in the particle in a box, you actually have an infinite number of solutions because you have the ground state, then you have the excited states. And of course there's an infinite number of excited states. So these are the families. This is a single family with an infinite number of solutions. So on the next homework, which I have you do, is I have you do this calculation, and so this will be the ground state, and this is not the ground state. So that's here. How about I do it like this? I'll call that I, but make that the ground state J, and J is not I. And what you'll find is that is always 0. That's always 0. And of course, if J is equal to I, then it's normalized, so of course it gives 1. So as it applies to here, well, why wasn't this 0 or 1? It's because these, remember that my representation, this is like the wave function of a Hamiltonian, this is like the wave function of a different operator. They're not in the same family. So they can be, I mean, they're the coefficients, they're these coefficients, but the coefficients could be anything. And also, another thing I pointed out was, and I literally did this, when I made that handout, the one that I actually printed out, when I took a thin wave, I kind of made up my own particle in a box. I made it really thin. That's not really a valid solution. I just made it up. And I then decomposed it into a bit of this plus a little bit of this. Those amplitudes, those weighting coefficients were from that. That's actually how I did it. So anyway, like I was telling you, professionally I actually do this, even if it's to teach a class. So, any questions? We're all okay? So, I'm just reviewing. I always like to review a little bit, so I'm just reviewing a little bit backward. But again, that's why it's nice for you guys to come by office hours, because I think that's something I definitely needed to review. That would have helped if I wrote the problem set a little bit better too. But now I know that next time. I taught 342 12 or 13 times. This is only the 5th time, so I'm still actually rough around the edges a bit. Now, also, so this is the first question on the next problem set, that you're going to do an overlap integral within the particle in a box family. Recall last time that now what the rest of the homework is all about is about these flat potential surfaces, where you have wave functions in different regions, and they have to be equal. Let me emphasize x equals 0. That's kind of important. So what I've done is I've given you a whole bunch of potential energy surfaces, and you have to do this. You've got to make sure that they're continuous, that's the first one. And you have to make sure that they're smooth, and that means that the derivatives are equal. And what that does is that gives you an ability these will be like A e to the ikx plus B equal B minus ikx, and this will be C e to the ikx, and yada, yada, yada. So what these do is they allow you to solve for A and B and whatnot, and C and D, and then you can do then once you have that, then you can solve for energies and whatnot. You can solve for whatever you want to. Last time we talked about how you can get 3 limiting cases. You can get, you can observe some really interesting behavior. If you have a low energy wave, it won't penetrate the barrier, in which case it'll get reflected every time. Now this little crude quantum mechanical model doesn't allow for doesn't allow for the particle to be smashed into the wall or anything. It's just, I mean, it's not like some supercomputer model of a car hitting a wall, right? So because of that, there's nothing in the model that says it gets destroyed. I didn't add that to the Hamiltonian. So the reflection is 100% if the energy is below the potential energy. Recall that if the energy is just enough to hit the barrier, it still doesn't reflect. The amplitude is just completely flat, so you still have 100% reflection. And if the energy is high enough, what you end up with is this behavior. Sorry, I didn't give myself enough room. In which case, it stops reflecting, and it'll actually start to transmit through the barrier. So this is percent transmission. And what is, again, unusual is that classically, that means if it was a car, you get all or nothing. It doesn't break through the wall to 100% until it has enough energy, and then it always goes through the wall. And again, that's what we call classical or Newtonian mechanics would stipulate that. Once the ball goes over the barrier, it would, of course, go over the barrier and keep going. But in quantum mechanics, the two things that are weird are the fact that the ball can still go through the barrier slightly with too low energy. It still bounces back though. But if you have enough energy to cross the barrier, sometimes it'll bounce back anyway. And as like some of us were talking in office hours about the homework, sometimes I can give kind of a nice explanation, hopefully it's a nice explanation about why things make sense. More and more, I have no explanation for this. I have no explanation for why something would not go over the barrier if it has enough energy. Other than we are, last time we solved this, it's some hideous algebra, but we did solve the percent reflection. We did it as a function of the momentum in the energy barrier. And plug in numbers, I've done that here, E over V. I guess I need to worry about the mass, it's called the mass of the electron. Anyway, blah, blah, blah. You can plug in numbers and you can see that the percent reflection is not 100% if you have enough energy to cross the barrier. You can do the calculation, here it is, this is the result. What's the explanation? I don't have one, other than this is the result of the calculation. I just don't get it. I don't get why that happens, but it's absolutely true. Now, so let me give a couple more examples, and then you're going to do many more examples on your homework. And it all just comes down to continuous and smooth, make the wave functions equal, make the derivatives equal. Nothing is worse than doing the derivative of a sine or a cosine, or I think I have some e to the x's. I think I have an e to the minus x squared as a wave function. Not that that's a hard derivative to take. None of that's too bad. Let me show you two other examples, and one of them I have on the website. I have a solution on the website. The other one I don't, so maybe I'll write that up. I kind of feel like I owe you one or so last homework. So two other very famous examples. Now here's what I could do. Here's what I could do on an exam. I think we have 2.5 weeks till the next exam. Kind of uncomfortably close, really. Okay, so here's the flat potential, but the barrier is finite. So instead of the previous example, it's called the finite barrier problem. It's the infinite barrier problem. This is the finite barrier problem. Okay, what I could do is I could ask you to set this up, but of course I'd have to give you some information such that in region 1, you should know that there's, how many regions are there? How many sets of wave functions do I have to solve? 3, right. So there's this weird one here. I'll make it a little bit wider to give myself a little bit more room to write about the wave functions. Okay, in region 1, you really don't know what to do until I have to tell you that, the great turkey created the universe with this weird barrier with a single electron that the turkey threw at the barrier, and the barrier is to the right, so you should know that you've got a right traveling wave that's going to hit it. oh, it's going to hit it, so it's going to reflect, and you can see that there's always a reflection. You can imagine that if the energy's not high enough, it may always reflect. Even if it is high enough to cross the barrier, it's still going to reflect. So you hopefully know that you're going to have to include a reflection wave, and A over B will be, I'm sorry, B squared over A squared will be the percent reflection, and it will have to be continuous and smooth to the wave function in region 2. Okay, now this is where this part actually is kind of fun. Okay, now, if it gets through, and it will always to some degree, even if it doesn't have enough energy, the only thing to note is that you're going to have, you've used up A and B, so you go to C. Hopefully you realize that the momentum is going to be less, right? The momentum is going to, you have to basically shave the potential energy off the total energy. Okay, but is there a D wave? Now remember, there's a forward wave and a reflected wave. Now obviously there's a forward wave because even in the case that I drew up there, even if there's not enough energy, it always gets into the barrier a little bit, even when the barrier is infinite. So it definitely is going to penetrate even when the barrier is finite. So that's this part. This is the wave getting into that barrier. But is there a reflection?
Yes.
Left shark, what do you think?
Well, maybe not, because I don't see how it could be reflected back.
Now remember that, right, in the infinite barrier, the wave function 2 was just a C wave. It was C e to the I kx because I never said it reflected off any other barriers. Right? So now what do you think about this? Is there a D wave? Is there a reflection?
Yes.
There actually is a reflection. There is. But where is the reflection coming from then? What's it reflecting off of?
The inner surface of...
Oddly enough, yes. Yes. This part. The drop in potential, oddly enough, it will reflect off of it. So what waves do, you think of them, hopefully, this isn't too quantum mechanical that it blows your mind, that things reflect off barriers. What they're really doing is they're reflecting off changes, right? So the wave hits some kind of change. It's a change in potential energy. It reflects off of it. It will reflect off any change, even a negative change. So the presence of a barrier is a positive change of potential, but it'll reflect off a negative change of potential as well. Now, I actually have an example. You look at a black car, painted black, like super black. All right, this is a Porsche. It's a $80,000 car. I'm looking at the hood. It's perfectly black. What do I see?
Purple.
You see a reflection. You see, but now hold on. Doesn't black absorb light? Black, the definition of black color, black paint is that it absorbs all light. So how can you see a reflection? How is that possible?
The gloss on top of the paint. Some of it reflected on it.
No. There's no such thing as perfect absorption because of this behavior right there. Actually, yeah, there's like a gloss layer, so when it bounced off the gloss layer in the interface between the black, but it's the same phenomenon. It's the same phenomenon going on. So when you have flat black, which you really don't see a reflection, what it is that the surface is rough. They have particles in the paint. So that's flat black versus gloss black. That's the difference, by the way. Okay, so you actually have a reflection wave. Okay, now what about region 3? What about region 3? Okay, I'm up to the letter E, so I'll give that much to you. Well, here. Right, so it's obvious that there'll be a... What K, though? K1, K2, K3?
K1.
It's K1. It's K1. Okay, now let me explain K1. This thing has... Okay, let's say the particle is here. The probability it's here depends on the amplitude of A and B. Now, it has a certain amount of energy. There's no potential energy, so the K is determined on how much energy it has. Now, over here, you may have thought that, okay, well, it had to penetrate this barrier, and it shed some energy. And when it came out here, it has less energy and therefore less K. Does that sound okay? Huh? What do you think? So again, the Great Turkey created this through the particle at the barrier. You know that the barrier, it's shed some energy, so that's why K2 is less than K1. There's less momentum, there's less energy, because there's a barrier. All right, that's high school physics. When it comes out here, then there's still less potential energy. There's still less energy because it shed some on the way. What do you think?
The same medium
Left side. What do you think?
It's gained back because of the drop.
Well, that's one way to think of it, yes. It's still the same K. Another way to think of that is that the total energy is constant, right? The total energy is constant, so there's no potential over here, so it has to have the same K. Now, what you expect to be different, now notice that I tried to trick you by saying, oh, but it sheds some energy when it goes to the barrier and comes out here. That's actually reflected in the amplitude. So what you would get is this behavior. Let me give let's say that the particle doesn't quite have enough energy to get through the barrier. We know that there's an exponential decay. All right, so here's a nice wave. The wave doesn't have quite enough energy to get through the barrier, but before it decays to zero, it goes through. It has the same frequency, but it has less amplitude. That is a reflection of, that accounts for the fact that this barrier is a Bisnocker. That it messes with the particle, but it doesn't decrease its waviness. That's dictated by total energy, which is the same left and right of the barrier. It just decreases the amplitude. Okay, now you can imagine that reflection is reflection, but what is way more interesting is percent transmission, which will be E squared over A squared, these amplitudes. And how do you solve that? Yeah? Remember what's the name of the game? I got that there, I got this there. So that the barriers of length, there's L linked to the barrier. What do I do? Huh?
Start solving for A.
Yeah, left side, you guys are quiet. How do I do any of these problems?
Carefully.
Carefully, what's the first step? What's the first step?
Boundary conditions.
Boundary conditions, right. Set e to the I, a e to the 0, that's 1. A plus b is equal to c plus d. Do you see that? Right? Because I'm at x equals 0, I've got a plus b is equal to c plus d. Now that's the continuous. What about smooth?
First derivatives.
Right, set the derivatives to 0. So I've got two equations. A plus b is equal to c plus d, and that's because I'm at x equals 0. And then I've got a ik1 plus minus b ik equal to ik2c plus minus ik2b. So I did the derivatives in my head. Okay, question.
Like for the boundary conditions, are all three of them would be equal or just the two?
Now I only have, now I'm talking about one boundary, and I have two regions in two different ways. So I've got 1 is equal to 2, and x equals 0. They are equal, and their derivatives are equal. So that gives me 2 equations and 4 unknowns. And that's kind of sucky. Notice what I just said, 2 equations and 4 unknowns? Uh-oh. Now what have I got over here?
Another 2 equations.
2 equations and 3 unknowns. C and D and E. Now it turns out that it's ultimately solvable because you see what I'm doing? I'm actually, so I've got 4 equations and 5 unknowns. 1, 2, 3, 4, 5. It's not ultimately solvable. But notice that the only thing I could ever care about is a ratio of 2 unknowns. So what you can do is set up these 4 equations, again, smooth and continuous, 2 barriers, two places, so that's 4 equations. You can solve them for E over A. You can solve them for E over A. That's how you do the problem. You want to do it?
No.
Yeah. Look at the seriously, look on the website. I didn't print this. Why didn't I print it out? I did it on the handout. It's on the website. Why didn't I print it out? It's 5 pages long. Right, didn't this sound like a nightmare? 4 equations, 5 unknowns, and then you have to solve for a ratio. How long? It's systems of equations. Those are kind of painful. And we did it with up here. It took me the entire board.
What's the fourth equation?
Continuous and smooth, continuous and smooth. Right. Wave functions equal, derivatives equal, wave functions equal, derivatives are equal. And so this one bridges A and B and C and D, and this one bridges C and D and E because you're trying to get A and E into the same equation. Again, systems of equations, right? So you're going to have to try to eliminate, you have to put A and B in terms of C and D. C and D is put in terms of E, and that allows you to put A and B in terms of E, right? Right, by combining equations. Right, now already you should be like, well, that sounds like it might take a while. Right, it took 5 pages. So I do the algebra on a handout. It takes 5 pages of algebra to do this, by the way. And I'm pretty sure I did it. Okay, maybe that there's some slick willy algebra ways to do it in 4 pages, but I wouldn't say more than that. So I'm not going to do it in class. The main thing I might ask you to do is, I might set up something like this. Hopefully you followed along about how you set it up, but now you can also see why. I mentioned this to you before. Quantum mechanics, there's actually a limited number of questions I can ask, because you can think like that barrier problem, the infinite barrier problem, which was a little painful, but not, I did it in class. It wasn't like completely mind-numbing. And then I just, well, it just comes to an end. It's mind-numbing. It's 5 pages of algebra, and I do this for a living, and it took me half a day to figure this out. Right? So I can just make small changes to quantum mechanical questions and all of a sudden, kabamo, your head's blown off. So anyway, so look on the handout. Now I'm not saying that I would want you to figure out the algebra because even I don't know how I did it. I know I did it, but that's all I know. But in terms of like, yeah, but so anyway, so there you go. Let me show you one other, and then I'll show you some times that these actually show up in real life. I haven't ever done that yet, which I feel really bad about, but I thought I'd try to just shove all the quantum into you. Okay, so this is an example of a thing. Let's turn the infinite, the particle in a box, to the particle in a finite box. Right, it's like the inverse of that, right? Now this guy, let's do 0 to L. Okay, so there you go. This one here, actually, as much as my particle in the box wasn't that bad. It's sine, when I center the left side at 0, this ends up being sine n pi x over L, right? It was actually really similar to the Planck distribution. When the barrier is no longer infinite, it's way harder. Oddly enough, it's way harder. Now, in this region, the solutions are a e to the I kx. See, it's no longer necessarily sine or cosine. Oh, and I'll have to have a k1. But let me explain why. Okay, now, the ground state is still going to be like this. It's still going to be like that. Well, what about the edges? What do you think about the edges? Now, before, when the barrier was infinite, the wave function has to be 0 at 0 and 0 at L. Those were boundary conditions that I used to solve the wave function. What about in a finite box? What do you think? Do they still have to hit 0? No. All right, so here's what happens. They actually leak out a little bit. They can leak out a little bit. And that means that you've got other regions out here, and these will be the same. So I'll just do the right-hand side. The left and right are the same. These are going to be C e to the I k2x. Actually, no. You know, I do have to do this one because it's moving the other way. So I have to put a minus, right? So if this wave gets out, it's going to be moving to the right, and if it gets out, it'll be moving to the left. So I really did need to write that down. Okay, and then you solve it for smooth and continuous. It actually is. I don't have this problem worked out on the website. It is. It's fairly difficult. It's about 2 or 3 pages, and yeah, there you go. What is especially kind of damning about this one is that, okay, so here's the ground state, here's like the first excited state. I didn't draw that very symmetric, did I? Here's the first excited state. So again, you see the difference is that the wave functions kind of leak out a little bit. Oh, what else? I can tell you something else. Okay. Let's say, this is just an intuition question. I'm just throwing this at you, just for the hell of it. Okay, so there's two wave functions in the trap. They have energies. And maybe I'll do all the solution and post a handout on how to do it. Again, this again is multiple pages. I can certainly compare that to an infinite trap, what we've been doing the last month. How do you think they compare? Do you think that these energies are greater or less than the infinite box? Is the finite box have lower or greater energy or the same energy as the infinite box?
That one is bigger.
You think, no, okay, this versus this, I got one vote for this is greater energy. I'll do it like that to remind you that. Okay, I got one vote that this is greater energy than this. What do the rest of you think? You kind of the same or less? Less. Okay, now what have you said great? Why do you think this one's greater?
Because, like, I feel like it's higher, like the wave. Can I just go up there and like explain it visually? Or I'm not supposed to the camera. Anyways, so I feel like it's higher, but the endpoints push it up. So where the starting point is, but the endpoints don't really matter much in the overall if you're looking at it.
Well, now I think I can articulate this a little better. The wave function dips into the potential energy, so it picks up potential energy here, right? Which would increase the energy.
That's what I'm saying.
Yes, the wave function dips into the potential energy, whereas before it absolutely couldn't, because it didn't pick up infinite energy, which it cannot do. So the wave function dips into the potential energy region, and that raises its energy to be higher than this. But you're actually wrong. But there's two effects. It dips into the potential energy, which is energy raising, but there's an energy lowering effect here as well. So there's two things. This is the one that's different. I have to focus on this. Two differences. One is that it leaks into the trap, which is energy raising, but there's an energy lowering difference as well. What is the energy lowering difference?
Kinetic energy?
Yes, it's wider. It's wider, and wider always has less kinetic energy, which is part of what you did on the last homework. It's wider, I have greater uncertainty in position, I have less uncertainty in momentum, and that means it actually has less kinetic energy. And the damnedest thing is that actually wins. So this actually has less energy because the energy lowering, widening of the wave function slightly, it's not slight by the way, it's slight. It slightly overcomes the energy raising of dipping into the trap a bit. Okay, so that's interesting. Now you can't know that unless you work through this. And again, I don't want you doing we do this to grad students, by the way. You go to grad school, solving this is one of the first questions you have to do because you're paid, right? You're paid to take quantum mechanics for grad students. And I expect you, look, you're being paid, right? It's not unreasonable to ask you to do a 5-page proof. Now, here's another interesting thing to run into this. What happens when the energy is greater than the potential energy? It turns out that any energies, so remember, ground state, excited state, I don't know, maybe there's 2 or 3 more, but something really interesting happens if the energy is greater than the potential. Maybe it's like this. What happens is, again, if the energy is greater than the potential energy, it's going to do what you're used to in those other guys. You get less amplitude and lower frequency, but it goes on forever. And there's no more quantization. There's no more quantization. So you get ground state and first excited state, maybe there's 1 or 2 more because of boundary conditions. But here, the boundary conditions are actually loosened up a bit. And so what you find is that, let's take a spectrum. Let's take a spectrum of this.
Professor,
Question? Yeah.
you said the graph that we've been explaining has less energy because it has less kinetic energy because it's wider, which means there's less uncertainty in momentum, which means higher energy?
No, it's less energy. And now, hold on, there's 2 things. It's wider, which means that it's less curvy, it has less kinetic energy. You could also say that there's greater uncertainty in position, less uncertainty in momentum, which also is energy lowering, which is part of what you did in the last homework. So the fact that it's wider, on multiple ways to look at it, it has less kinetic energy. Now, but it has greater potential energy. That's countering that. It has greater potential energy because now it's leaking into the box. And if it has amplitude in the potential energy region, it gains energy. It just doesn't quite, I normally would think that they balance out. They don't. They don't. The loss of kinetic energy surmounts the gain of potential energy, barely. So these actually have a little bit less energy. So it just is. Okay, now, let's do another thing. Let's take the so this is an electron in a box. Let's shine light on it and do a spectrum. It'd be like a UV-Vis spectrum. UV-Vis spectroscopy is electronic spectroscopy. When you shine UV-Vis light on a molecule, you're looking at its electrons being excited, versus infrared, which is you're looking at the vibrations being excited, which aren't really quite so connected with the electrons. So if I was to do this, absorption, and let's do this versus wavelength, which remember is inverse energy, what you would see is the ground state being excited to the first state here, but then you would see something like this. This species would have an absorption spectrum like this. Now the reason is that the ground state can be excited to the first state, and these have very well-defined energies because quantum mechanics does that. So that's this energy here. And I don't know the scale, but this is all made up anyway. But you see this well-defined transition of the ground state to the first excited state. But then when you go to the higher states, you wouldn't see sharp transitions because anything goes. When you're above the potential energy, anything goes. And let me maybe try to draw that a little bit better. So again, when you're above the potential energy, you don't have sharp states forming anymore. You have a continuum of states. So here, I'm just redrawing that and giving myself a little bit more room. So we have a ground state, a well-defined ground state. We happen to have a well-defined first excited state. After that, because after that, the next energy is above the potential energy, you end up with stuff like this happening. I have to think about it, right, before I draw it so that I don't mess it up. Okay, so you're thinking like this is next. Now, in case you're thinking, oh, well, the next state is like this. No, the next state would be slightly wider than this one. Slightly wider, but just barely. See that? And then the next state is just slightly wider than that one. Anyway, and the thing is that there's no, I can make this higher energy actually be more narrow. I screwed up. Isn't that right? I screwed up. It has to be curvier. Sorry. It has to be curvier. Let's say that the next state is this one. My bad. Sorry about that. Brain just fell out for a second. Okay, so this is the next state. Okay, however much energy that is, let's call it an EV. The next state can have 1.0001 EV. The next state can have 1.002 EV. Anything goes. Because the next energy state, let me not screw it up this time, would just look something like this. Right, so I drew that with slightly compressed, I compressed it slightly. The next state, again, would arbitrarily be a little bit less, now I'm exaggerating it, it would have a little bit higher frequency. Right, so hopefully I didn't screw that up. So beyond the potential energy, any energy goes. And that's why in an absorption spectrum, you would see this continuous absorption from, again, ground state to first state, but the ground state to the second, third, fourth state is continuous because I can draw any wave function and satisfy boundary conditions and everything is fine. So, we're okay, you see all that? Questions?
So basically, once you're out of the box, you can cut the distance between your spots an infinite number of times.
Well, you can kind of think of it like it's like a freeway. It's like a perturbed free wave. So notice, basically, you notice what I'm doing, I'm drawing free waves, and free waves can have any kinetic energy. The difference between this and a true free wave is that the wave amplitude is higher in the box. So it's kind of like, so imagine that we have a free wave, and I see I'm out of time. Imagine you have a free wave, and that's, of course, a flat line with no potential. And here's a wave, oh, it's a happy wave, maybe it's a sine or something. Now imagine that I put a dip in it. I put a dip in it, a really shallow dip. What's the difference? You would just build some amplitude. You just build some amplitude, that's all you would do. Because it would want to be there. It wants to be near the dip, but it's not really that different. And so that's kind of what I'm drawing right here. Anyway, this